So what is a sample? Well, a sample is a subset of the population. All right, so if we define the population as this group of stick figures, well, more or less stick figures, they're all different colors. They kind of look genderless to me, but anyways, if we say that this is our population, a sample would just be a subset, a smaller group of that population. All right. Now, the important thing about this sample, well, there's a couple of important things. One is the sample, by definition, is always going to be smaller than the population, right? A sample can never be bigger than a population. How would that work? Okay, a sample can't be bigger than the population it came from. And if the sample is the same size, in other words, you've got everybody, all right, then it's no longer a sample, it is the population. Now, I suppose you could say the sample is n minus 1. If n was the total number of people, let's say that there are 50 of these stick figures. A sample could be 49. N is 50, the size of your population, minus 1, 49. You could say that's a sample because you don't have everybody. But usually samples are quite a bit smaller than the populations. Usually it's not just, one less than the population. If it was one less than the population, I would say, what are you doing? Get back out there and go get that missing person or that missing animal. All right. Okay. So samples then are always smaller than the populations they came from. And ideally, we want this sample to be representative of the larger population. Okay, we want this to be a good mirror image, kind of like you might be familiar with this, the gold, Austin Powers movies like Goldfinger, Goldmember. I forget all the names, but this is Dr. Evil, and this is Mini-Me. You can think of Dr. Evil here as the population, and Mini-Me is the sample. Mini-Me is the mirror image of Dr. Evil, only smaller. All right? So that's what we mean when we say that it's representative. All right? The sample should look just like the population, only smaller. So there are blue people in the population. We want blue in the sample. There are red in the population. We want red in the sample. And that's true for all the different colors. What if our sample was missing one of the colors? What if it was missing the pink, for example? Then we would say that the sample is not representative. It's biased. It would be biased against the pink people. All right? It would not be a good mirror image. So again, to be representative means that whatever characteristics appear in the population, they also appear in the sample. Now, you can appreciate that might actually be hard to get, right? How do we get a sample that's representative so that, if there are a gazillion characteristics in the population, that we have a gazillion characteristics in the sample? We have fewer people, but those characteristics are still there. Well, what we do is we generally try and take large samples because, and this has been shown repeatedly over and over again, at least theoretically, it can be off a little bit some of the time, but generally speaking, the bigger your sample is, the more representative the sample will be of the population. All right, so what we're saying here is you're better off trying to increase sample size if you want your sample to have a better chance of being representative of the population. All right, so bigger is better when it comes to sample sizes, but even if you get a very, very large sample, it's not a guarantee. All right, it's not a guarantee that your sample is going to be representative. Now, you might say, well, okay, if bigger is better, how big should my sample be? Should it be half the size of my population? Should it be 10% the size of my population? There really is no magic number, all right? What I can tell you, though, is generally speaking, the more diversity we see in the population, the bigger our samples should be to capture that diversity. All right. If it was a sample of clones, if we had a population of clones, then we don't need a lot of people in our sample because there would be very little diversity among the clones, right? They're not perfect clones, but they're pretty close. But again, if you had that much cloning going on, not a lot of diversity, you only need a small sample. But if you look at the human population with our, who knows, gazillion number of traits, if you did want to get a representative sample from the population, then it's going to have to be pretty big because we've got to capture all these traits. Okay? So that's kind of like some rules of thumb I've given you. Bigger is better as far as samples go. And if you've got more diversity in the population, you're going to want a larger sample size. But beyond that, there really is no magic number that we can just throw out for you. Okay. Another thing that researchers are going to try and do to get a representative sample is they're going to use a technique called random sampling. Now, if you could see me right now sitting in front of my computer, I would have my fingers up and I'd be doing those quotation marks in the air, random sampling, right, with quotation marks. And that's because when researchers randomly sample, they really actually don't truly randomly sample. All right, now let's look at why that's the case. Like, let's understand what it means to randomly sample, right? So if you are randomly sampling, what you're doing is you're making sure that every member of the population has an equal chance of being included in the sample. Rarely is this the case. For example, let's say that we want to randomly sample a group of Utahns, all right? That means that every single person who is an official Utahn needs to have an equal chance of being included in your study. Well, I'm betting that no matter where you live, you know somebody in the outskirts of your town, let's say. There's somebody, way out in the middle of nowhere, Modena, Utah. Is Modena in Utah? Okay, Parowan. Somewhere on the outskirts of Parowan, there is somebody who is off the grid. There's no way that they have an equal chance of being included in your sample. Okay, so when researchers say that they randomly sampled, they really have a loose definition of what is random. What they are really doing is using something called convenience sampling, which means that, let's say they have access to all the people in Utah. Well, no, sorry. They don't have access to all the people in Utah, but they have access to the people on the campus, SUU campus. They're going to randomly sample from the SUU campus. Now, that's not random sampling. You're not randomly sampling from Utah, like the whole Utah population. All Utahns don't have an equal chance. But those that you have access to on the campus, they have pretty much an equal chance of being included in your sample. So when you choose somebody, that was the wrong word. When you test somebody from campus, you're not deliberately picking them out of the crowd and saying, I want you because I think you're going to give me the data I'm looking for. You randomly sample from all the people on campus, all right? So convenience sampling is kind of like a hybrid. You randomly sample from the people who are convenient to you, all right? And we use that as our definition of random. Like when you see in a paper, if they say participants were randomly sampled from students on campus, you know that that's really convenient sampling. Okay? Okay, right, so a convenient sample then is where the researcher randomly samples from the members or the people of the population that he or she has access to. Okay, random sampling does not guarantee that the sample will be representative of the population. In other words, we can't assume that because we randomly sampled that our sample is going to be unbiased. Weird things happen, right? You might even have a huge sample and it's, convenient sampling, but it was random within the, members of the population you had access to. But it might be a huge sample. Maybe it's 50,000 people, 500,000 people. And it was random. There's still no guarantee that it's completely representative and unbiased. No guarantee. It's highly likely, but there's always that slim probability that you missed a characteristic or something like that. All right? Okay, now let's go back. Now that we've understood a little bit more about samples and populations, descriptive and inferential statistics, let's try and figure out what we can and cannot do with the handheld and the power tools. So let's look first at descriptive statistics. So these were the ones that, they're the Polaroid camera shots. They're taking a picture just to give you a snapshot of what's going on. So you use descriptive statistics to summarize and describe a larger data set. So could you take a picture of numbers that come from the population? So you've got a population of numbers. Can you take a picture of those numbers to summarize them? And the answer is yes. For example, you could calculate the average in the population, the mean of the population, as long as you are calculating it from every single person or thing in that population, then you can say yes here, okay? So absolutely, you can, you can run descriptive statistics on the population. Can you run descriptive statistics on the sample? And the answer is yes. I can have a sample of students from campus, and I can calculate the mean of the sample, right? So descriptive statistics then can be calculated, where's my cursor, can be calculated on both populations and samples. Descriptive statistics can be calculated on any set of numbers, no matter where they came from. Now let's move over to inferential statistics, and let's look at a sample first of all. Can you calculate inferential statistics from a sample? Go back to the definition of inferential statistics. You don't actually have to physically go back. I will repeat that definition for you. Inferential statistics use sample data to tell you something about the population the sample came from. So did you hear that? Inferential statistics use sample data. So absolutely, positively, you can calculate inferential statistics on sample data. That's what inferential statistics do. They take that sample data and they tell you something about the population. All right? Only probabilities, though, not truths. Remember that? So can you calculate inferential statistics on the population? Okay, the answer is no. Think about why as I take a sip of water. Okay, so why can't we calculate inferential statistics on a population? Well, go back again to the definition. Inferential statistics are run on sample data. They're not run on population data. The reason why they're not run on population data is if we had access to the entire population, we already know what's true for the population. We don't have to infer anything. If we had every single person, animal, place, thing that we collected data on, if we included everybody in the population, we now know the truth. No inferences are necessary. The reason why we have to run inferential statistics on sample data is because we don't have everybody in the population. We must calculate statistics on our sample and then use them to draw inferences to the population. Okay? So again, inferential statistics are only calculated on samples and never on populations. If you had the entire population, you don't need inferential statistics. You don't need to make any inferences. You now know the truth.